Actually, I was gonna do babies first quantum mechanics, but the example that they gave us. I wrote about epidemiology for kids.
Epi what?
Epidemiology.
Oh, okay, about viruses. Right?
Yes. See? I can read my book also.
December, right?
You have to read it out loud. Yeah.
I did a. I don't remember what our options were. I think for the like kid oriented one, I did a magic school bus script about
Yeah, they
the
said-
chemistry of red.
No, I like generated. It's like I made nothing be here. And then we switched to mom. You're like, how many people?
Whew.
That also is yeah, makes the best.
Okay.
I don't know. I just have it saved in my MATLAB. If you open MATLAB, does it show up? If I open it, it just shows up right away. Like, yeah.
So who is ready for the presentation?
I've been.
I have no question.
That I would thought was correct is not what past person presents on. So now I don't know if I'm correct or if they're.
Or they all are incorrect and you are the only.
No.
It happens sometimes. So for sure we need to go this as a minimum. And anything else which is missing. I think read everything is quite clear, right? No.
Kind of. Well, I just have a couple questions, but like I can wait, I guess.
But
If you wanna like go over what you
if you
need,
know
we'll wait for like the end of class to ask.
if you know how to shape your presentation, just start making it.
I've been trying.
Okay,
Yeah.
Is it like a salute or you
I have Melody in my name, Blue, and everyone else.
Cause that just, it just comes from the dance, it just continues on.
Yes.
It means
It
nothing.
has no connotation. Okay.
Same, that's on my minor, right?
If I would be so organized, not to put you in blue, then all my notes will be typewritten. That's it. Okay, so let's quickly discuss if there are like emerging questions. Okay, and then I will rush through to do everything for Elsa, right? Because not because she's so special. But although she's, but because her, like everything we do is cool and useful, but her presentation is an image of our research project. Basically, in the projects, we will do the same as Elsa, just 3 times less. She's doing, yes, she's doing 3 projects in 5 minutes, and each of us will do 1 project for a month. Right? Okay. And the application of the code to oscillator is one of the next homeworks. The most recent that I announced. Right? So
Can you repeat that, please? Sorry.
The application.
Okay, yeah, all right.
yeah.
Yeah,
That academic system sometimes have assignments below the data. Sometimes include homework.
yes, I'm aware of that.
Okay, and by lucky coincidence, the third part of Elsa's presentation will coincide will overlap with a big percentage with your homework number the last announcement. Okay. More emerging questions. Well, you just- you prefer to behave like in the movie scene, with that, take popcorn and entertain.
I don't know how. I'll try my best.
Please go ahead.
When you talk about normalization of wave function in discrete representations, I want to talk about normalization. Does it really mean normalization in normalization sense, like for a wave function or the probability density should be one? That what it means? Because I do not understand in discrete representation what it means.
I completely understand your question and your confusion.
Yeah.
Mm,
Because normalization of wave function, I could just talk about that. When you about the discrete representation.
Let me just focus cameras that you included in this thing, 'cause otherwise it looks like a voice from above. And this is a very tiny thing compared to what we need to accomplish today. So, integral of absolute value squared for the wave function not equal one, otherwise it will have no sense. But there is much more deeper importance in normalization. So technically, normalization is procured by having square root of tx when you declare initial function. And it will secure that everything you do will be normalized. But the meaning of normalization is if anyone takes expectation values. Well, just I will also do version. Well, we all do expectation values, and if the wave function is not normalized, then expectation value will be wrong because it is divided by normalization. So just if the normalization is twice as wrong, then the result is twice as wrong. Okay?
Yeah, yes, that's normalization. Well, I do understand in discrete representation.
Have you been here last Wednesday? So it was all covered. Wave functions are represented in like discrete space of 200 points or whatever. That's it. And we replace integral by summation. Yes?
Yeah.
That's it. Okay. And I think this was covered in previous years. Really well. Who did watch last year's
I didn't.
Last year's one.
presentations on wave functions?
Oh, nice.
Okay, who didn't? What?
Watched 2 years ago. I
Yeah.
couldn't, when I, well, no, well, I mean, but I didn't watch 2021. Because when I clicked on that link, it took me to your like YouTube account to like edit it. Like I couldn't, obviously I couldn't like do anything with it.
You can open it, see when you.
Oh, I just went to like the years prior before that. Yeah.
Oh, the earlier years are much better.
Oh, okay.
Yeah.
This year students are excluded, but general trend is this year it becomes worse and worse and worse.
I
First year is-
hate to disappoint you by breaking.
Please disappoint me by showing that this trend is wrong. Okay,
Okay.
more emergent questions, or you are ready to lean back, take popcorn and enjoy. Okay. So the plan is to focus on each of these three problems, and we need to do it at any rate. And then as time allows, I probably will return to questions for formality, which are important, but not as practical. And okay, anything else I need to plan to cover today? So Sam, I think for your presentation, everything was delivered. You can just sit and prepare it, right? Patricia, you can also start preparing. Eva, what prevents you from completing the slides?
what prevents me.
Yes. So for position we covered in class, momentum is maybe momentum. So if time allows, so we will do 1, 2, 3, 4, and then 5. Momentum forever. And for Fred, this is just this image.
Yeah, I get something like that,
Okay.
but it looks really weird compared to, also compared to like what's in the video,
Okay,
where it's not,
try
hard to explain.
try to visualize initial wave function. Psi naught. Plot real psi naught. Plot imaginary psi naught.
I have all three parts. I figured out a code. But I get this like irregular,
No, that's fine. That's
that's
fine.
fine.
Oh,
Even
yes.
if it's, okay, all right,
And the
perfect.
density of fringes depends on the value of momentum. If you take higher momentum, they will oscillate much quicker.
Okay, so. All right,
So you can choose them.
Oh, yes. It will be your main task during the projects.
yeah. And
Yes, keep.
I feel like I should definitely know this. Can you like briefly explain, I understand probability distribution and how it widens, but there are like the two graphs here, right? This is
Position,
Probably.
position, expectation value of position in the
okay,
middle, and the top one is width uncertainty of position.
okay, so neither of these are
The
potential or probability.
correct.
Oh, man, well, then I don't know how to visualize this.
Okay,
Oh, wait, I think I have probability,
okay.
but
So
figure it out.
let's discuss them. Please prefer your questions. I just want to really do things that are critical for completion of the whole year class and projects, and then you cover things.
All right.
So, by now it was executed for free. WD. Is it? Now, I will, what is the first task for forever? Well, not forever. Yes, forever.
Oh, goodness.
Just read how does it, how is it for me?
I'm sure it's in a box.
Box?
Well, one of them is.
The,
Sure.
box, oscillator, and the first one,
Application of wave packet code to box, finite and infinite.
okay.
You
Sorry,
just do like finite box.
that's right, box. So I rename the code, WP box. Make sure that it is here. Yes, and now I'm going to say, maybe code box. Now, the potential energy is set to 0. So I need to find, here is what I'm going to do. By the way, let's check if we are getting recorded. Yes, we are getting recorded. I am going to find where CHEM2 is defined, and then track back where okay, yeah, here it is, line 117, diag V, and we need to find where V is defined. I will just scroll back. By the way, for melody, please remind me to return to this lines later. It is important for your presentation, but a little less for the rest of the class. But this thing W prime times POP times W is something very unique that no one else in the class ever did. You'll be a pioneer.
All right.
So breaking down V. Scrolling, scrolling, scrolling. Scrolling, scrolling, scrolling. V equals X times 0. Yeah, definitely it is 0. And now I do need to have it redefined. So bet I uncomment line 64, V equals barrier 2, and barrier 2 is defined here. So no, it won't work. It will not work. Okay, so let's plot. Let's discuss what this line means. So I will go to the command window, type this one, and figure and plot area 2. So the part of the code that we are discussing right now does chop the universe, and universe is maybe a little bit too ambitious, onto 3 segments. So we do have simulation cell from minimal initial to final. And before, when we were looking onto the free space, the potential was 0 everywhere. Now, if you want to describe a potential as we did for particle in the box, we need to have potential equals minus infinity in the middle, or plus infinity here, plus infinity there, right? And we need to define borders. So we need to find, I don't know, I don't have fantasy like y and y prime, the values along position where we make this jump in the potential, right? Clear up to now. So how is it represented? How can we write it down mathematically? We can tell that potential equals, and one more thing, we can be general, not in a military sense, but generalizing idea. So we can call these regions like 1, 2, 3, and tell that here we will have potential U1, which we can set to 0 or plus infinity. Here we'll have U2, and here we'll have U3. If you want particle in a square box, we can put U2 a very small number, or like we just need to tailor this values, and we need to specify these parameters. Okay, so let's get back to the script.
Okay, real quick, I am having trouble running it. It's giving me an error. I don't know if I typed something accidentally. wouldn't let me-
Did you change the
Not yet, not anything intentionally. It just said there is an error in this line on ADA.
Try to just percent.
Yeah.
See. Okay, so favorite help from Melody to all of us, at least to me. Back to the subject. So, Elsa, how do you interpret this U1, U2, U3, X2, and AB? So let's discuss these three parameters. Not three, five parameters. U1 to 3, X2, and AB. Can you tell what are they on the so if it's
Is the X2 minus AB, does that go with like the positive values? So
yes,
not like the negative infinity?
so
part of the
U1, U2, and U3 are just values of the potential, right? X2 is the midpoint of our simulation cell. AB is half width of the or width of this box. So X2 minus AB will be this point. X2 minus AB, right? Center minus width. Second point will be X2 plus AB. And then the width of this thing will be 2AB. And this parameter should be set somewhere. Make sense? More or less?
I think so, yeah.
Okay, now and modify things. So U1 and U2, U3 must be, let's do them plus 0.1. Since it is atomic units, even fraction, even 0.1 will be something big. And here we will do minus 0.1. See? Close all images. And rerun the script. So, yes. So we did set up, you see, U1 and U3 are above 0. U2 is below 0, and wave packet is moving from outside of the box and then trying to pass through the box. What we can interpret it as the electron is trying to pass through an ion or through a molecule, so like a ion. And then since it is attractive, there is a chance that it will reflect back, pass through, and get caught right in the middle. So right now we did start the parameters. The box was too small, and the electron was away from the box. For this problem, it would be more interesting to maybe start the wave packet inside the box, and make the box deeper, and see a situation when the electron doesn't have energy to escape. So let's quickly remodel this situation. then please try to repeat it and run, okay? Everyone is invited to do it as well, but always, how do I say? Primary client.
The primary client.
When not only I, maybe some other people, when losing credit card and coming to a bank, telling them, give me a new one immediately. They don't. We need time to print, but if you need something to use immediately, they just pull it and prefer customer instead of the name. And it is valid only for 5 days or 10 days. So I want to make it deeper. So instead of -0.1, I will do maybe -0.5. Here +0.5. And now, you see, when packet starts at X value 30, and the midpoint is about 48 something.
What part of the code do I paste into the command window to get that to run? Lines like 56 through 59, or well, for 60? What lines of code do you have running in the command window?
I understand your question, but it disappoints me a little. I need to cool down.
No, that points you.
Right. Okay, so we all are consecrated programs, which means we do not paste individual commands into the command line. We modify the whole script and write it. Okay. So we rename the script, save it, but before it was called VP_3, for instance, now we save it VP_box. So we modify lines, whatever, 57, 58, 59, save it in VP_box, and we run this new script. Do not paste anything in the command line. We just modify. Okay, and I use right an intention to use things from my command line. Now to have things bigger, one can just push the green triangle. You see, there on the top, run. So as soon as the script is ready, it will run and it will run. Make sense?
Yes, mine does not look like that though at all.
Let me finish a little demonstration and then I'll probably walk through the sheets and make sure everything is happy. Everyone is happy. Okay, so I'm modifying parameters of the potential, and I also want to go to the beginning and reset the initial position. Need to reset X naught. X naught 30, and I want to have it maybe 48 closer to the middle. Now save, erase everything. Again, erase all panel of these images. And now run over. So right now, we start with packet. You see this greenish potential became deeper and higher at the sides. We start with packet in the middle, and you see that both are so high that most of the probability of the packet doesn't have energy to escape. So we trap the electron in the box. We do not see this nice eigenvalue because we didn't up the port to. We just see the dynamics similar to what we did when we let it move and have this function where and down. So let's quickly make sure that everyone is who is interested is able to reproduce this little image. So I'll swiftly jump through this.
how to create the box,
Huh?
how the code for the box.
So AB equals 7 is set up at the very beginning. And then this lines 57 to 60 do set up the barrier, the potential, and then V equals barrier.
So I got all these.
Okay, let me just inspect. Okay. Then this B next continuum means. This command does. I had a password whatever I told would be or when you do it.
I do not. I haven't been following along, but
Okay. I'm going to work another. Can we work another version?
I'm
We're going to change.
a little confused, shame learning.
Let me instead of, I will prefer speaking to you, but speaking to computer.
Okay.
So it's still running, right?
Yeah.
That's.
Sorry, my computer's a little stupid.
It's smarter than myself.
Oh, I guess this doesn't know what I'm going on here. No. Yeah.
We need to place those from the side.
Oh, okay. Got it. Oh, thank you.
I do not have it actually.
Oh, you do your more important search. Okay.
I'll learn it from Elsa.
Yeah, chain learning is the best way to do it.
Oh,
Yeah, let me talk to you. I can- Talk to you. Cool down. Elsa, would you please tell Patricia why I'm doing this way? Why I'm disappointed in the first thing where they are looking at. Tell what was wrong with your approach.
Because we're not supposed to be copying and pasting it, we're supposed to save it as a separate file and then edit it and then save it again and click on the green, run button instead of copying and pasting.
Many things. I strongly appreciate it.
Ships in Star Wars.
Yeah. I don't know if that's low enough.
Well, looks like a firefighter. Sure.
It's a two sugar spot coffee back there.
I'm both overheating and sick job.
Actually, rules you don't.
Yeah, can you explain that? Because last time I asked you didn't, oh, you still. I thought maybe you still, I thought you still did.
No, I know, I don't need to prove it to myself, I will be.
Okay.
Word here. Green triangle.
Oh, Sam, our rotation student, Ben, right now knows what your, what he is from, your gaming.
Oh, really?
The tan one?
He said, I can't remember what it's called. What's it
Space
called?
station gaming.
Yeah, he was like, I'm surprised to see somebody else wearing Space Station Gaming merch.
Cute.
And I'm like, what?
Yeah.
It's like the sweater that Sam is wearing, yeah, it's like gaming, whatever. I'm like, oh yeah, you were supposed to before. And then I told Ben that he should talk to you about it, and he's like, no.
I'll come in and I'll start talking. about it.
Yeah, come in and talk to him about it. Many students are currently on rotation.
How many students are rotating right now?
A lot.
Do they just rotate it until they find someone they're interested in staying with, or?
Three on, three rotations. Three left.
We have 3 students.
Rebecca, no, then Ron, somebody else do this one. No, Max rotated last one. With
Oh my
Becca.
gosh, they go so fast.
Yeah.
Just when I get to know people. That's what I thought.
It puts it inside the box.
Someone joined our group earlier.
It's not line 948, okay.
U1 is plus 0.5. U2 is negative 0.5.
Yeah.
U3 is plus 0.5. Delete the percent sign in front of V equals barrier 2.
V equals barrier 2. Okay,
And then you add a percent sign in front of something else. I don't know what that is.
which one? What line?
You just have to say it out loud, I just have to remember.
Oh,
V equals X times 0.
sure.
Add a percent sign instead of that one.
Okay.
Anything very well?
Oh.
You want to see? It's so cautious.
How do you drink your coffee?
Thank you so much. With a lot of cream sugar in it and flavor in it.
And what is the script open for the?
What?
Oh,
I could have brought my
yes.
finger in the lab.
You should have next time.
Well, I'm a little carton of the whipping cream. But I don't use, but
I'm
I like brothers. Yeah. Oh, man.
I'm just trying to play.
Yeah, because every time I hit run, it must be wrong.
There's a lot of.
No,
I don't have any more.
don't have any more.
So, did I just solve that one?
Appreciate your time. Oh,
So,
well, uh,
stop sharing here and start sharing there. Who's disabled participant screen sharing? Am I so mean? Let me allow myself to get my guess. Focus. Okay. Share. Share. Okay. Box. Finite, infinite. Depending on the values of this U1, U2, U3, one can mimic Indian box, but this values are good. Next one. Barrier is very simple and it is very important. So, I will stop sharing and just make a little comment and demonstration. Erase your company. So, right now, the middle is lower than the sides, right?
Needle lower than the side, like how?
What?
And that's, you said the needle is lower than the side.
Middle is lower than the sides. Now, from this figure, I will keep only positions of this when we have a turn over into different values. But the actual values of U1, U2, and U3 will be dramatically changed. Okay, so what if I set up the potential in the following way? I will have U1, we can even have 0, then U2 will be higher than U1, and U3 will be lower or the same height as them. So this is position, this is distance or reaction coordinate, this is energy, potential energy. Do you have any connections to the regular chemistry classes or your chemistry research? Or
Yeah.
because you're saying something really smart.
It looks like some kind of reaction where you start off with a certain amount of energy and then you reach the activation energy and then
Plus
you release energy and you end.
M plus.
M+1, yes. So, did you agree with Valerie?
Yes.
She convinced you?
Yeah, it's a thermic reaction.
Yeah.
She did the same way as you, right? I don't need to explain it because I will play it even better than she did. Perfect. I'm just trying to speed up our class. By all means are available to me. So this is reaction.
Reaction or reactive.
This is
Product.
product. And this is activation energy, and another smart chemical words. Intermediate, right?
Yes.
Or transition state.
Yes.
Transition state. So here is your take-home benefit of this class. Of course, this little connection that you get energies of harmonic oscillator for partition function for your thermodynamics is academically useful, but this, to my belief, is much stronger benefit for all of you to take this class. So as soon as we do a little exercise in the next 5 minutes, you'll be able to model any thermal chemical reaction. So we can model energy of reaction, energy of product, and activation energy. And then by wave packet passing through the barrier, we can model a chemical reaction. Okay? You just need to learn energy of reaction, product, and barrier from elsewhere, or do an educated guess. Okay. So I am starting to share our script on screen. So let's resave the code. Instead of box, let's code it as a barrier. Barrier. And
When you resave these, are the previous like saves under the other names, are you still able to access that?
absolutely, yes, I just opened. If I want to save movies, and I can also,
So it doesn't replace the other ones?
no,
on your-
no. And as an example of disorganized person, my personal laptop is is a swamp of 3,000 versions of codes that I don't know how to navigate through. Okay. So let's set reactant is 0. Transition state is something intermediate, and product will be energetically effective, thermal reaction. For the exo, which one gives more heat than it takes? What's the right word? Exo is combustion, endo is something that doesn't go without heat.
Yes.
Okay. So I'm just saying, changing these three things. Or if you want to do academic study with boring things, you can put 0 here as well. And at the beginning of the code, I need to pull my initial position at a little earlier place. So 30 or 35. So we start before we start reaction in the region of space corresponding to reactant rather than product, or rather than transition state. So saving, erasing things from previous run. If I would be Elsa, I would save images from each previous run into PowerPoint and then show everyone this glorious history of doing the things like that. Here I'm just erasing and now running. So you see, there's a little barrier and this huge wave packet trying to approach. And you see, it goes a little slower than it would go through in a free space, right? So the wave packet feels resistance, and it does, instead of passing through as we had for wave packet, it reflects back. So this regime tells that the activation energy is so high that the temperature that we put into our reaction is insufficient to drive the reaction, right? So if we are true chemists and we really want to have this reaction done, and we cannot apply catalysis and lower the height of the barrier, we need to redo this reaction with higher temperature, right? Make sense? So I'm going to make another modification. All this, so I'm erasing this.
My graph did not do that again.
Let me do another modification. Let me do another modification, and then I will make a circle. So I will do just something more spectacular, so that we do not waste time on intermediate things. And by the way, you see this wave packet does show an image where it goes, like, it hits barrier and then it reflects back instead of having a straight line, right? You see. So I want to increase kinetic energy. I want to increase temperature. And here our kinetic energy is modeled by momentum. Higher momentum, bigger kinetic energy. So I'll just try to use maybe 75 instead of 25 and see what happens. Save. Run. Now it goes forward a little more vivid. It fills the barrier, but a portion of the wave packet is passing through. So by providing higher temperature, we activate the reaction. Make sense?
But it's still not a high enough energy to.
Part goes through, part reflects back, and then you have a yield of reaction, which is a rate of that pass through to the overall probability. So here by the next eye, it is about like 60% yield. If we keep increasing it, it will be close to 100%. Does that due to your chemical intuition?
Yes.
And by the way, this thing that comes at the last point is progress of a reaction. So initially it is 100% reactant, then it drops to maybe 30% reactant and 60% product. And then at the end, there is a region of numerical error that I can explain later why you cannot trust. But this code has a potential to predict outcome and yield of chemical reactions if you model energy of reactant product and transition state in a correct way. Okay, I'm going to make a tour over sheets, and those who are interested will make sure it works. I read a question in your.
I guess, I don't know how to like formulate it, like. I guess I'm just wondering what the significance of everything after that 60-30 peak is.
We do need to have a bigger box because we expect it starts passing through the walls of the box and penetrating into reactant area once again.
Okay.
So to prevent it, we just need to have a bigger box. And it is doable, but it will make calculations slower. Right now, for the getting purposes, we simplify and speed up. Okay. All right. And I think so it was, you did everything correct. Okay. Now we observe that the back reaction, but we cannot use it because we have a periodic boundary interest. But you modeled everything correct. And words that I answered to Fred are good common. If everything works at your side, you are 2/3 ready. To change learning, you need to.
Okay, I'm confused because like this part went right, but these graphs don't look like that at all.
You're doing fine.
Oh.
Your battery is too high. And the temperature that you want is gives only like 10% utilization. And then it comes here because it's like reflects back, so it starts demonstrating a numerical error.
Okay.
Because like each tool has its limits of applicability, and the setup of a phone as we did it right now are limited to maybe like first 30 because 10 seconds of the reaction. Later on, it gives errors due to too small cell type. Okay.
Okay.
You doing sorry. But you can modify it and make it run, right?
Yeah.
Okay.
Right.
Voila. Right on top. So we still have a little time. Now let's do last third of Elsa's assignment. And your all assignment for the last announced homework. Study harmonic oscillator, right? So here is our sandbox and playground, right? We should remove all the things and stop this defining potential as piecewise discontinuous function. Instead, we can just define it as V equals m omega squared delta r squared over 2. And we can set it up as so either m omega squared or rigidity constant, and then we need to set up the equilibrium position minus x squared divided by 2. So we need to set up where is the center, and probably center of the potential can be placed in this with the center of the simulation itself. Elsa, yes?
Yeah.
Good, thank you. So start sharing.
Dimitri, for those graphs that you have up, you said that they are like the back reaction, but that they're confined to something. What was it that they were confined to?
Related to periodic boundary conditions. Okay, before we go to oscillator, let me return to let me do another demonstration. Just if I become too excited, please remind me to return to oscillator. So, so I will increase momentum even higher, and I will set up the potential equals 0. So reset potential equals 0. Save as instead of barrier, I will call it PBC, periodic boundary condition. I may have made this demonstration, or you may did it before, but let's try it once again. So I set up potential 0 again, but increased momentum dramatically. Let's see what happens. So it goes quicker, right? And the specific question, what would happen if during our simulation time, the wave packet will approach the wall? See what happens? Can you explain by your own words? Huh? It doesn't bounce. It's same as your instructor tells goodbye, it appears through the wall, and suddenly you see me appearing through the wall again, right?
It goes through the wall?
Yes. So it is just
Repeats itself.
exactly. So this concept is called periodic boundary condition. So is what was repeat your question?
You wanted 0.
Oh, yes. Actually, 0. So periodic boundary conditions. And here is most spectacular thing that illustrates it. So if you look on the distribution of the probability over time in space and time, right? So before we had a straight line going and slowly like a straight line going forward. Now it hits the wall, right? And at the same time it reappears from the other wall. So it keeps momentum unchanged. But we confine space to a little simulation style. We can set up a lot of discussion to provide a justification for this trick. Justification. Okay, yes, we were on the photo. But it is a necessary evil that may be a little unrealistic, but it prevents us from much bigger errors on other side. And there are two ways to model chemical reactions, either to have very, very long vacuum to the left or the right, or have a little smaller simulation cell, but allowing to disappear boundary conditions. And attention to the way how the momentum generator program is responsible for having this theory boundary conditions involved into our simulation. So let's ask this question. Why am I telling about it?
I'm not really sure.
Okay, but just remind me to return to harmonic oscillator. So, do you see these little things on the top and middle panel? So expectation value of position increases along line, and then suddenly drops and continues over. Right?
Then it goes through.
Right, it reappears from other one.
Okay.
And the width of the wave packet, it should grow quadratically for free space, right? And it does. But then when half of the wave packet is on one wall and another one, we have an artificial peak because the width is bigger than the size of the box. So we cannot trust the cone at the instant of time when the wave packet is passing through the wall. We need to have it, but as for the time before wave packet hits the wall, we can trust the result of this fluid. As soon as it approaches the wall, it becomes doubtful. And the ways to avoid this error, either to reset the box bigger or explore smaller energies and shorter time. But if needed higher energy longer times, one can just expand the box. Make sense? Enough? I wanted to say something to Melody. Do you remember how we defined momentum operator as a method? Like one can has zeros onto main diagonal and then having -1 and +1 inputs 1 over delta x. So by acting by this operator on the wave function, we minus phi a bar, we will implement momentum, right? Do you remember? More or less. So if you see, we need to compare two elements, first and next. We can skip the center main diagonal to increase precision, but we need to have two finite elements to model a derivative, right? But if we approach the very first line or the very last line, we have like -1, 0, and here 0 + 1. We are missing 1 point. Where to take it? Because then our definition of derivative is wrong at the first and last. So if we add a little 1 at the end here, a little -1 at the end here, and a little +1 in there, it will mean that as soon as the wave packet approaches the border, we define momentum by comparing finite differences from opposite sides of the box. And if this +1 and -1 are added, then we do have conservation of momentum, which is a fundamental law of physics. If you do not do this thing, then there will be another error by violating momentum conservation. Right now, momentum is conserved, but we are limited to certain times. Enough? What did I ask you to remind me? Thank you. So I'm going to arrange. CS harmonic oscillator. Save. And now if it is not pre-made, oh, okay, it is here. So I will percent out this thing. And you see here is the pre-made like x minus 40 squared. So it will be like an example of quadratic function in line 66. So save, and maybe I will, yeah, let's run it. Right now it is too ambitious, too high momentum. Maybe it's a little bit less. Save and run. So it goes, and then instead of continue, what happens to it? Yes. And what happens to it width? Do you see any change over the width, right? In free space, width was increasing. And here it is basically
See it slightly moving.
slightly, but to some degree, it's basically the same.
Maybe a little further apart.
So it goes forwards and backwards, right? And it's the wave packet performs this oscillation, right? So the expectation value of position behaves like a sine function, or combination of sine and cosine. And if you run for a longer time, or then it will perform a larger amount of oscillation, right? The width, the dashed line is just a reference point from the particle in the free space. If we select it and erase it, then you'll see the width performs oscillation. Basically, it's your homework that is due next week or whenever, last announced homework. And if you remove this reference point for strength that was done for offered for free space, then we see oscillation. So the position performs oscillation with one frequency, and width oscillates with double frequency. In some sense, it's answer to your last announced homework. Elsa, are you ready? Things are working?
So,
With,
yeah.
from my point of view, you're ready to prepare your slides more sufficiently. If there are any questions, just get back to me. I will answer your wishes, my will. So, what do we do next? We completed our minimal task, and now let's be more ambitious and see what is next on the plate.
Do you have anything else to say regarding mine?
Oh, yes. So melody commutation of operators. Conversion of operators between momentum and position. Let's decide what others will be doing when melody will become my primary client. So just prepare your slides, right? I need to describe something for melody, and I apologize if it will be too complicated and too boring for everyone in the class. But we need to go over it. Okay. So if the rest of the class feels bored when I'm talking about it, just wait when melody will be talking about it.
Yeah, more boring.
Okay. So sharing
I go to the bathroom real quick before we start.
all this. So questions and
I have a
answer
question,
sessions.
Can you give me a rundown of how to visualize potential in this, with this code? Or,
Absolutely, yes.
okay, because I'm lost, honestly.
This is the perfect time to ask this question. So
Awesome.
we'll keep it secret from now.
Okay. I'll tell her about it.
You'll tell during the presentation there. Okay. So I hope I didn't erase. Yes, I didn't erase things yet. So, do you see this figure 1?
Yes.
Which of the lines correspond to potential? Which color of the line corresponds to potential?
Green.
Okay. So we just need to find them.
The dark.
Yeah, whatever. We need to find a part of the code that plots this dark green.
Okay.
Okay.
Well, what would be the difference between dark green? I know it's a disappointing.
Really, no, it's not disappointing. No. I think this hard question is assigned to Patricia. Yes. Let me quickly check if it is true, and then we'll return to the question of that. Yes. Alternative methods to compute quantum dynamics. And by the way, but Teresa, what I just by answering to a question, I don't remember whom, but last thing we were discussing about periodic boundary condition is also your part. Yes. So that there is a chance for wave packet exceed the box and reappear from other side. So alternative methods. So asked by Fred.
Well, it's for me too. I got it, but yeah.
When I will be talking to Melody, it will be covered over again, but very good. I can close my messages.
Yeah.
No worries. Yes. Globally rating stars of global size. You can set high standards of reference. Really try to use the view of your model. What a anything to know, right? So you want to record something people to predict reaction. Okay?
Yes.
You're not arguing this.
No.
And the measurement from instrument and prediction from computation must coincide. Right? If everything is done correctly, measurement is correct, and if computation is correct. And sometimes one can observe that there is a disagreement. Either someone was doing what errors in the third account, or there are errors in the code. Not because of there could be errors because of the regions and lack of attention, error, and there could be errors which originate from wrong method, or method which uses too many approximations. And if there is no direct experiment to compare with, then the only way to convince ourselves and future reviewers of your publications that the results are correct is to get agreement between different methods. So you want to use the same observable by different methods. And if they agree, it's not absolutely true, but it is a good sign that everything is done correct.
Okay.
So this code, that calculation with two different methods. And this method, you differ by the way how the momentum operators are programmed. And basically comparing these two different representations of momentum data, the main transport model. So whenever you done us answering your question, we will get that. Okay?
Yeah.
Clear enough.
Yeah.
Okay, now your
There were three.
one method is used. Method number one is applied only for momentum space and is set up to demonstrate only vectors. Only this space. Method two and method three are used. And they differ by the way momentum rate is over in Cartesian in predicted space. Momentum method number one uses momentum greater in the momentum space.
Okay.
It's possible to do any model by this method, but then you need to convert potential into momentum space, which is a little crazy even for professional theoretical physics. Method two and method three are both in predicted space, but they split the region for space in different ways. Three momentum rate. Your other thermal, I thought it would be quick thing
That's all right.
to go, but how to cause the protection. So
I got the probability.
wait, let me answer about
Well, I
plotting the
got the
potential.
probability.
You do.
Yeah.
But I'm also a human with limited possibilities of parallel thinking.
Okay.
So focus one thing at a time.
Okay.
Okay, so we need to see how the green line is plotted, right? So the red and dark green are wave packet predicted by different methods. And there are CHEM2 and CHEM3, GTAO2, GTAO3, right?
Yeah.
And Psi2 and Psi3. So those are based on them. Green one is basically the variable V, which is a potential. If we set up a new figure and type what V, we will have just a potential.
Yeah.
If you would do it, if Alpha would do it in a previous run, you would see the step function, right? For the reaction for the barrier. Now we did set up things to demonstrate harmonic oscillator. So it plots the potential, right?
Okay. Yeah.
Basically, your question is answered, but we want to track down where this plot V is implemented in the code, right?
Yeah.
So let's every cool things will be hidden inside the main loop. So we need to scroll between 171 and 259. So I think the line 191 is providing potential V. Just for better visualization, it multiplies it by 0.1, not to decept audience, but just to show apples and oranges on one screen, because absolute height of potential and wave packet can be different. And then how do you recognize that it is green? So three numbers that encode the color can be interpreted as
I have no idea.
did anyone who works for print shop? Photography? Graphic design?
My sister does.
Okay, ask me. So how do we transfer power figures in a digital form?
I don't know. Based, I mean, I don't know. I just know I know about like the grid where they got all the different colors.
So we have
It's easy to figure out a coordinate on the grid.
These are- they have different values of each one
Okay,
that
yeah,
corresponds to the color.
Like,
No,
or
it was
orange
one.
or red.
So. Repeat this abbreviation,
RGB,
which stands for,
red,
no, how you can encode the color of a pixel by screen number.
Oh, you just change the color, like, it's up to T55.
But we need screen number, well, one can encode if you like, play Z spectrum games or Atari or like old fashioned, they have less color. 16 colors.
Yeah.
But yeah, but there is another way, instead of scanning over all colors on a line from 0 to 56 or to whatever you display to like several million colors, one can just continuously change screen number. RGB, what do we mean?
red, green, blue.
And each number changes from 0 to 1. If we have RGB code 111, 100% of red, 100% of green, 100% of blue, which color will it be?
White.
Yes.
So by mixing all basic colors in equal proportion, we are going to get white or approximation of white color. Right? Brightness goes to maximum, 100%. If you have RGB code 000, which color? Okay, if you have RGB 100,
Red.
Oh, wait, no. Well, because there'd be no red.
no,
It's
100.
It's 60%.
RGB 100% red, 0%.
Okay, that makes sense, but then why is, if you add 100% of all three colors?
It's like light, if you have.
It's like a freeze.
Okay.
Rainbow combines and goes white.
all right.
Of course, if you be some way of gray, because nothing is perfect in our world, especially when humans get to the height. Right? Now, what will be the 0, 1, 0?
Blue, yeah. Well, no,
0, 1,
green. Green,
Okay,
yeah, then-
now let's look into line 181. So color point one.
Mostly green.
So yeah, it's like
Yeah.
dirty green.
Yeah.
Do you agree that it does correspond to this green line?
Yes.
Did you answer?
Oh, that one?
Yeah.
Correct,
The problem.
Okay,
Okay, did you answer your question?
yes, I understand, but, I'll have to figure out how to get it.
Now you are speaking with the same intonation as I was doing my doctoral defense. And it was
Unsure of yourself? So, okay, this potential here is constant.
because you are doing free space.
Okay, I understand. Do you? Okay, no, I get that. Huh? Well, it's constant potential in like a free space. Is the potential 0? Yeah,
There is no potential energy in free space. Electron, no one
yeah,
there to resist this electron. It moves where it wants. There are no other objects. No one attracts, no one repels.
okay, yeah.
Constant equals
But it
zero.
is, yeah. Yeah,
But
you
it-
have a constant 0.
constant equals zero, but
Well, because it could be
Even-
0 at one point and then.
even if one raises or lowers it above or below zero, gradient of constant force will be zero anyway. So absolute value doesn't vary. Okay, back to melody. So the toughest question, right? How your question is formulated?
I don't have a question at the moment.
No.
Commutation of operators and the conversion of operators between momentum and position.
Okay, conversion between momentum and position is not easy, but it's clear for me. Commutation is maybe easier but more challenging. So let's look for, I don't know which one to offer earlier. They both are important.
Lines 106 to 115.
Yeah. Okay, this is second part of your question. So, stop the camera. Stop sharing. And if you guys are not interested in what I'm talking to Melody and you have an idea how to prepare your slide, do not waste time because time is limited, right? Do your slide. So, Melody, I need to admit this expression is correct philosophically, but it is not what is programmed into the actual code. We can plot, we can visualize the momentum operator and see that it will be a little different from this one. So what is, and this is method, this is momentum operator in position, in position space, right? So this derivative is applied to wave function that is expressed in our regular space. Now, if you would, I'm going to erase, if you would set up the momentum operator in momentum space, then it will be minus zero delta k plus delta k 2 delta k k max. So it will be just values of momentum on the main diagonal and zeros everywhere else. So momentum operator in momentum space will be a diagonal thing. Okay. Now, because we are humans and we feel a little challenged to think in the momentum space, we need to convert this operator from momentum space to position space. Can I erase this little writing?
Yes.
Okay. And I hope we are on recording. I cannot guarantee because sometimes things happen, but hope very much. Now, we do a conversion from momentum to position. Did we do it in the class? Did we do in any homeworks?
I'm pretty sure we did.
Yes. Can you remind me which equation should I write?
I don't.
You can.
So momentum operator is, it's
Not operator. We did convert in the past. I'll give a little hint. In the past, we did convert wave function from position to momentum space and back from momentum to position. Let me give another hint if it doesn't click yet. We were looking for solution for motion of Gaussian wave packet in a free space.
also a little while ago.
Yeah, but you remember playing wave in the middle of the night, right?
Yeah.
So the wave function as function of position at time t. If we predict future, the summation of expansion coefficients, eigenfunctions which will be plane waves, right? E I k x. And if we do not like k, we can put p over h bar, but it is the same. And then e to the power minus I over h bar, energy, eigenenergy times time. You're grand, you remember.
Yeah.
Now, And I will return back to kx because it is less fixed right.
Why is the, thing we now having minus omega c?
Your question is very legitimate. It slows down our story a little bit, but it is very legitimate. Can you please repeat it?
Extends the plane wave. You gave the question for plane wave, E equals to high kx. Or normally once the equation for the plane wave is that I normally say that you stand in classes, ikx minus wc, omega c.
Okay.
Right.
How about energy equals h bar omega? Would you agree? How about omega equals E divided by h bar? How about having here omega? Okay, I return back to original writing, but your question is answered, right? Now, word since we do have index, the index by momentum, we put index k, right?
It'd be this.
And what is c sub k? So it is our wave function at time equals 0, right? E minus I k x
Then there was
d
the,
dx, right?
Yeah.
And here we replace summation by integral over dk. So here we do integral over position, here we do integral over momentum. And this is a concept of a next after Fourier transform, Laplace transform. Okay. So we do have from momentum to position or from position to momentum. So we can generally put right now for at times, I will remove this thing,
Okay.
your favorite. And I put here just a function psi of k gives psi of x. So from momentum to position. And here we start from psi of x. I just forget about time. And we get psi of k. So we go from position to momentum and from momentum to position. We have Laplace transforms of the function between these two spaces. So those things act for functions. Functions can be saved as vectors. But now our task is to convert operator from momentum to position. So now focus on me. I will just ask the question. In order to convert wave function, which is a vector, I need to apply the e to the power ikx and integrate once, right? But operator is like direct product of two vectors. How many times I need to multiply by e to the kx, and how many times do I need to integrate? Yes, perfect. So let's evaluate it a little bit more. So if we think about wave function as a vector, right? In different exponents, then this I and this psi of k x1, x2, and this wave function will be depending psi of x1, psi of x2, and so forth. Here it will be psi of k1, psi of k2. So this integration and multiplication by this thing can be analyzed as a multiplying by a matrix onto this vector, right? And this matrix will have two sets of indices. One index will correspond to value of momentum, another position, and we can call it W. And here the same integral over dx and e to the minus I kx can be considered as the same matrix because of minus W star, right? So to convert a vector between position and momentum, we apply this matrix of transformation between position and momentum W.
Okay, so when you're converting from position to momentum, you use W star.
Yes,
Okay,
if you convert only a vector. Now, I'm going to erase this thing, but to continue the thought. The operator in momentum space can be represented as a dialectic product, right? And then, like, column times row and column times row, right? So this is our P operator in momentum space. Now, if you want to convert it into the position space, we need to perform by a way as if you would need to convert this vector into position and this vector into position. So we multiply it by W from the left to convert this one, and we multiply it by W star to convert this one. So P operator in Cartesian space will be application of Laplace transform twice from front and from the back. So it will be a combination of three matrices. In the middle, operator of momentum in positions in momentum space, and from left and right, Laplace transform between position and momentum. It was your second question. And now we need to go to your first one. Is it sufficient enough?
yeah,
Okay, let me illustrate this thing.
So that was that's called the conversion.
Yes. So you see Px equals W prime times POP times W. Right?
oh, okay.
Okay,
yeah,
so we
yeah.
go from momentum to position. And when we do it, it will be a little bit different from what we originally expected as three diagonal matrices. We can visualize it. So if I go into command window,
Wait,
just a second, I would erase all these things. I just want to do a little demonstration. Here. And now I want to do mesh. Real Px. One thing, and I want to do mesh imaginary. So this is visualization of the momentum operator. When we were defining it by an equation, we thought that it includes subtraction of the elements which are closest to the near diagonal. And there were 1 and -1 away of them to mimic the I'm just going to approach the screen and see something. So those were your 1 and -1, which I needed to implement the periodic boundary conditions. And here, one element is positive, another is negative near main diagonal. But if you carefully do this Fourier transform, it means it includes second and third and higher orders to implement the derivative in a numeric way. So it uses next and next and next neighbor just in a little less proportion to demonstrate momentum operator and to implement derivative operator in a more precise way. So this is method number 2. And momentum operator is implemented as px. If we, do you want to ask something?
Yeah, so can you go back to the code? So, 115. So the apostrophe is to signal that it's W star,
Yes,
right?
it is both both. It's Hermitian, favorite word of STEM. When it is transposed and complex conjugated at the same time. Okay.
So does it matter the order in which?
Yes, if one swap this apostrophe, it will everything will be garbage.
Okay, because I'm just wondering, because it's the other way around when you wrote it on the board.
I'm a human and make errors. You
Okay,
just get extra credit to find my errors.
okay. So what's written in the code is,
It's correct. Whether I'm saying it
Okay.
wrong. And here how it is implemented. So we do have just imaginary unit, and then we have powers along x and along momentum. And then we have this basic element into this combined power. And then together we create this transform operator, which combines integration and plane wave. So plane wave is different frequencies. So, and this plugs into CHEM2 for px. If we use, like here is a question that I feel myself lazy to study, but what does mean purpose? So you can find it in Wikipedia or in MATLAB help and explain to all of us. But px3 is a momentum operator defined in a third way. So it will be different way to define momentum. And if we try to plot it, so px3, we see it is a little bit more closer to what we meant by using only nearest neighbors. You see, one is positive, another is negative, and there is a -1 and +1 at the sign. So which method, 2 or 3, is more correct is an open question. Now, how do we decide which method is correct before running any application? Remember a question from Patricia when we were grading your homework. Can we cancel momentum and position operators and subtract each other? Can we just put factor 2 up front? No. So computation of position and momentum should give a unity operator if they are programmed correct. Or there is no guarantee that it will be done absolutely right. And if anyone feels we are coming to like threshold of 7 p.m., if anyone feels you are ready to prepare your slides and I'm not telling anything interesting, feel free to depart, disconnect, and provide. The goal is to make presentations. I will stay here and do additional comments, but it is not mandatory to stay here. Okay? So if you're staying here, you're doing it on your own free will.
so the commutation of momentum and position should give the unit,
Imaginary unit.
oh, imagine.
Imaginary unit. So it may or may not give the right result. It may or may not be exactly imaginary unit, but a test how close the commutation of position and momentum reproduces imaginary unit is a good test to tell if we implement momentum operator in the right way. Okay, so let's do this little experiment, and then you will present it to everyone in US. You were the discoverer of it. So. Let's check if we have variables home. No. Home one. Let's two. So let's do home 2 equals px times hop x operator minus hop minus px. So it is a commutator, right? Now let's do this visualize home to commutator of position and momentum in the second method. So it is something interesting. It is close. The important thing that it is close to, it is maximal on the main diagonal as it should be, right? But instead of being constant for each value, it is ramping up. And let's check the real. And the real is also ramping in the opposite direction. Okay. Now let's do forms 3. No, wait, it should be multiply, not minus. It could be wrong. Okay, let's see. But so imaginary one has nothing in the center and some noise at the side. If you do the real, again, nothing in the center, noise at the side. So with all respect to method 2, it kind of fails the test, right? So the commutation is reproduced forward. Now let's do form 3 for commutation of momentum in the third method and position operator. So imaginary of form 3. Look at here. It is zeros everywhere, and it has something good close to diagonal. Maybe not exactly on diagonal first to subdiagonals, but it is much closer to what it should be. Let's check for real part. And it looks absolute zero. So we expect that commutation of position and momentum must be imaginary unit. And for method 3, it kind of reproduces what it should be. So method 3 is from some perspective is expected to be more trustable, although it is a little easier to implement. It's just main diagram. Okay, let's check how we are progressing. So we done commutation of operators and we done conversion of operators between momentum and position. So now that you are done, you are ready to prepare. Eva, any requests, any questions? Do you want to be a how it is on credit first preferred customer? Yeah.
I mean, I guess I don't really know what's going on, but when I try to. So for the computation of the expectation value of momentum, when I try to plot, like there's a plot that the previous years have tried to make where it's like the expectation value of momentum over time. And then when I am typing in what I feel like they typed in where I'm not getting the same graph.
Okay. So best example to study momentum over time is Olympus slope. Because even if you didn't solve it by pen and paper, you know that when it hits the wall, momentum becomes zero. When it returns above the median, it has maximum momentum, probably then it stops, and then ramps. So the momentum oscillates in the opposite phase compared to position. Like if position is assigned, then momentum is assigned. So we have an intuitive vision of what it should be, right? So let's select the setup for harmonic oscillator and try to plot expectation value on one hand, and on another hand, let's watch how this goes. Okay. And it should spend another 10 minutes. Just plenty of time. And then I think you'll be done.
Yeah.
And then you guys, the rest are welcome to stay, but if you have more questions after this, then you can, or if you think you don't have questions, you are free to do your schedule stuff and some other things. 10 minutes, you are preferred guests for that.
Yes.
So,
What is that? Yeah.
I know what to say and which area of the scripts to focus. I just need maybe a few seconds to refocus. Just a side comment, whoever loves chemical reactions and needs the yield of the reaction may look at this PO2 and PO3, which shows like how the proportion of reaction progress changes from 100 to reaction yield. So the code lines 232 and 233. When stop sharing. Focus on our favorite area. Remember when Melody was a champion and Eva was a vice coach? So expectation value is integral psi operator psi little star dx. And if you are not sure if wave function is normalized, to be guaranteed normalization, you just put psi star psi without an operator dx. So this will be a normalization. Right? So if we need expectation value of momentum, we just rewrite this expression and replace A with minus I bar T dx. Right? Or if we are programmed, then we will plug here either P sub x for method 2 or Px3 for method 3, right? Okay. So what do we see in line 233? AP for average momentum equals psi 2 prime, which is a conjugate times px times psi 2 divided by norm, and norm is defined in the previous line. I kind of believe that normalization is done correctly, but just in case to be sure. So it's thing like going into public lot, purchasing the year-long ticket, and at the same time paying at the entrance. So to have a double guarantee that you have a permit to enter. So for the third method, norm 3 and AP3. Now, if I would try to plot AP or AP3, I will see nothing. Because those are just a single variable. It shows the expectation of value of momentum at a given instant of time. And I'm interested to see projected how expectation of momentum changes over time. Right? So to do so, I need to accumulate values that is observable along the trajectory. So AVP2, AVP2, AP2. So this line 239 increments the array AVP2 each time we pass through, and at each point of time it saves into this long array current value of the expectation value of momentum, but it takes it not replacing by A, the length of array increase. So if I want to plot the expectation value of momentum by second method, I need to plot AVP2. If I want to plot it by third method, I need to plot AVP3. So let's real. You see, it oscillates. If the code was launched for the harmonic oscillator. Another little observation. At least I'm not overestimating my role in the world simulation progress, but in the example that I did run, and maybe you did the same initial values, the initial value of momentum was 0.75. You see, it starts here, and then it goes forward until it stops, and then it returns backwards, and then it stops, right?
Yeah, mine doesn't look like that.
Okay, let me stop by the C and check what it's doing.
Just like the plus this. And then it, yeah, then it keeps plotting this. And I
I'll tell something to everyone and then we'll talk about it in practice. So when the dependence of expectation value of momentum upon time will be very different depending on the model that you're studying. So it is dramatically different. It's like when you do I don't know, I don't remember which experiment you're doing, but depending on which sample you put in the instrument, you get dramatically different spectrum. So if you are doing harmonic oscillator, it's one thing. If you are doing free space, then momentum will not change over time. It will just account, right? If you were doing like barrier, it will be constant and then make a jump when it hits the wall. So it could be different things. So I suggest you use set up for oscillator because it's very predictable. And because it will be much relevant to last announced format. Okay, so I can approach your computer and make sure that we are modeling standard. This one is labeled in potentially. Who's inside the covering the split? Supposed to go. Because spring, maximum spring extends, and then push it back. Or whatever, came towards long gates, but then there was a third. Anyone, really with tow and then tow between one of several stations. Now it shows. Starts 75, goes forward, returns. But these more
No, that's one of the graphs that pops up.
so
Is there, there's no
we
video?
have, the program is complete. Okay? Where
Yeah.
is the camera? Thank you for supporting this gesture. But if there are more questions, I can stay here and answering.
I guess the only question
Really?
I'll try to avoid wheels as much as possible, maybe sitting at home or in cafeteria. But if you want to go, just send me an email, we'll set up a meeting or whatever. I really want to go. You're not alone.
Do you teach any Tuesday, Thursday classes?
Oh, no. I do. I think I don't show up to any class, and no one finds me.
Halfway through, so.
I do. Wait. So, meetings. That's Thursday, 4 p.m. And it is scheduled for 2 hours, I think it will go up to 8 p.m. It was, like,
Lots to talk about.
huh?
Lots to talk about.
Yeah, just group members just sitting and chatting and, you know, relax atmosphere.
Yeah.
So the formal part goes for 2 hours and then 2 hours. And on Sunday there is a departmental seminar. But let me know one consultation. Anything like,
Will you look at the information that I have and
you can send me your preliminary version and check like if it is enough. If it is enough, I'll tell okay, well, actually, if it is not, I'll suggest it. Are you showing me something?
No, I was gonna put it in my backpack.
Because you are doing it so, how to say, formal and official, written like. Yes, it's probably be to the quick, table content, you probably need to learn, more of analytical cases.
So for visualizing and observable, would that be something like position, physical coordinates? Like the graph of time over like, you know, the corner brackets X, like,
what?
is that not an observable, like, is your, okay,
You can just do more general program, even if not for the moment, the code has other observables. Like
yeah, okay,
or-
so.
or something before.
Can I kind of combine two of them then, where you ask to visualize and observable and what like group, I forgot what it was exactly, I have a picture. But like to group your data. Bundling groups of observables, that's it. So could I like just include this, say,
Yeah.
hey, we have like 2 observables here,
You can find a line of the code that shows several panels at the same time.
okay,
And you can some, cool.
all right,
And for making videos, you just pick up.
I have that already.
Okay.
Yeah. I just used the video like from the base code where we just have that Gaussian like expanding. Is that all
You
right?
just show the lines of the code that are.
Yeah, yeah.
Because.
You only get one.
Like it three.
Next, your student will work your recording.
Man, yeah, that makes me feel bad.
You need to point to the camera and say, next year students, remember. my
Oh, I will, I remember it, right? But
Even if you know the names of anyone of your more junior, corner, if you name them, if you be very impressed, like maybe you'll be watching and suddenly see it.
that'd be really funny.
I talked to you from the part,
Would you think of,
do your homework.
I'm in inorganic with, Wyatt and Sibel and Nate Alfman. Remember
Oh,
that?
that
Yeah.
is available.
I wish, yeah, I wish I could see their presentation last year, but I don't know, the link wasn't working in the email.
Send me,
Did you guys get
if something doesn't work, it's thank you, I will
like
like.
last year's presentation?
Like, yeah, we know it.
Like, did you see them?
Some of them, and then some of them, like the link server, so I just go on your YouTube. account.
I started with the oldest ones.
Okay. You want them to,
Yeah, the first couple ones
Like
are
what,
fine.
2017?
reason one of them is, in a group, very few, that maybe he will come and see how his example was old.
Yeah, mine's okay. You go first or second?
Somewhere in the middle.
I don't think they're always in the same order.
Because the amount of, especially is different than you try to, different amount of, five slices. Depending on all the friends. Do you talk with Siri on, iPhone?
No, there's not set up on my.
It's not very difficult, because some pre-made answer, but you try to answer the main code divider zero.
No.
It has some
Should I try it?
pre-made joke.
Really?
How do you divide by 0? Five divided by 0. Well, just another fine. Well, she says, imagine that you have 5 cookies and you split them evenly among 0 friends. How many cookies does each one of your friends get? See, it doesn't make sense. The Cookie Monster gets them all. No.
Oh, it used to be like, you don't have it in front of us or something.
Right.
Have a good night.
Why did you change it?
Right. Thanks for your dedication.